Alright, so last video we talked about the general ideas about the multiple regression, right? And then next, this video we'll talk about how to make the hypothesis test about the multiple regression. So we did about the hypothesis test about the simple linear regression, right? So we test about beta 1 to be equals to 0 or beta 1 not equals to 0. But in the multiple regression model, right, remember we have multiple explanatory variables, right? So that means we have more, not just the beta 1, we have more beta 2, beta 3, or something else, right? So here we'll talk about how to make the hypothesis test about the whole regression. All right. So before we do the hypothesis test, I want to talk about the assumptions first for the multiple regression model. All right. So for the multiple regression model, we still have 4 assumptions: the linearity condition assumption, the independence assumption, equivariance assumption, and the normality assumption. All right, so let's see the first assumption, right? Linearity assumption. So in the simple regression, we check the linearity assumption. We want to make the scatter plot, right? So we want to make the scatter plots between x and y and see whether there is shown any linear relationship or curved relationship, right? So we say if it shows a strong curved relationship, then this linearity assumption is not checked, right? We look for the linear relationship, right? Okay, so the same thing for the linearity condition for multiple regression. We need to check for each of the predictors. So we need to check for every explanatory variable you want to include in your regression with the y, right? So for our case, we have the bedrooms and the living area contained in our regression, right? So we need to check the scatter plot between bedrooms and price. And also I need the scatter plots between the living area and the price. All right, so here I will show you how to get these 2 scatter plots, or even though I have more than 2, right? What if I have 10 variables in my regression? How I can make the scatter plots together, right? So here, since this is the let's delete this, right? So this is the original data set, right? So we have living area, number of bedroom, number of bathroom, fireplaces, and the age of the houses as my potential explanatory variables, and the house price is my y, the response variable, right? So in our example, I used the bedrooms and the living area to include in the multiple regression, right? And I didn't use these 3. So actually I can check the scatter plots for each of them with the y together. So how I can do that? You use the analyze and say fit y by x. Remember, the scatter plot is the one the output that's first shown in your output, right? So here we still choose the price as the y, but for the x factors, I just choose all the variables I want to check the scatter plot, right? So for our example, we just check these 2, but actually you can add as many as you want, right? So here we just check these 2 and then just click OK. And then the scatter plot for each variable will be shown like this, right? So this is the living area versus the house price. This is the number of bedrooms versus the price. All right, okay, so this is how you get the scatter plots So we say for the first assumption, the linearity assumption, we need to check whether for each variable they shows the linear relationship between the x variable and the y. Alright, so this is a linearity assumption. And also next one, the independence assumption. Right, so for independence assumption, still we need to think about it, whether the observations are randomly selected. Right, so for example, whether this sample, these 1057 houses, are randomly selected. Right, so it will be for the independence assumption. And for the equivariance assumption, right, so still remember what we did for the simple regression. The equivariance assumption, we need to check the residual plot, right? So how we can get the residual plot for the multiple regression. Alright, so let's look at our data set and output. Right, so this is our output, right? Okay, still remember that? So this is the B0, B1, and B2, right? And then in this output, click this right triangle here. Alright, and then there will be some options. And then here, there is an option for the row diagnostics. Alright, so here it will the default will plot the effect leverage. We will talk about that later. And then next one, we have the plot actual by the predict. We plot the residual by the predicted. Plot the residual by row. Plot the studentized residuals. And this plot residual by the normal quantiles. So which one is the residual plot? It is the residual by predicted, right? So if we click that, it will show you the residual plot, right? So again, for the residual plot, we do not want to see the fan shape or the cone shape, right? So we do not want to see these two shapes. Then it will be equivariance assumption. Alright, and then next one will be the normality assumption. So for the normality assumption will be the same. So it will be either the histogram of the residuals, or we call it is normality plot, or we call it is normal quantile plot. Right, so let's look at this output, and then click this right triangle and still go to the row diagnostics, and there is an option to plot the residual by normal quantiles. Right, click that. Right, and then by the end of this output, you will have the normal quantile plot to check the normality assumption. Right, so again, we expect the points should follow a straight line, follow this straight line, right? But for this case, it is not follow a straight line, it is a curved shaped, right? So for this case, the normality assumption is not checked, right? So another way to check the normality assumption, remember, is to get the histogram of the residuals, right? So here it will not be like the simple linear regression with a the histogram of the histogram of the residual. So what you can do is click this right triangle and then go to the save columns, right? For the same columns, there are so many options that you can ask this jump to calculate for you, right? So here we want to plot or get the histogram of the residuals. So I just ask the jump to calculate the residuals. And then when we come back to our data, you will have one more column, which is the residuals. All right, and then I can make the distribution of the residuals so that I have the distribution of the residuals. I stack it. All right, then this is the histogram of the residual. All right, so either way will be okay. You can use this way, the normal quantile plot, or you can use the histogram of the residuals to check the normality assumption. And also for the equivariance assumption, you need to get the residual plot to see whether there is fan shape or cone shape. If there is either one, then this assumption is not checked. Alright, and then for independence assumption, you need to try check their randomization condition. Right, and then the first one is the linearity condition. You will not only focus on one scatter plot, you need to check the scatter plot for every explanatory variables. Right, so this is the residual plot, the same with the one we had before in our output. Right, so it's this one. All right. Okay, so this is the assumptions. Actually, the idea are exactly the same. The only difference is the linearity assumption, right? Linearity assumption, you need to check for every variable. And after that, you still get the residual plot and check the shape. You still get the normal quantile plot to check the normality condition, right? So there will be no difference. Okay, so then we should be ready for testing about the multiple regression model. Right, so let's go to our note. All right, so we want to make the hypothesis test about the multiple regression. Let's say regression model, right? Because the hypothesis test is always about the population. So if we talk about the population, we talk about the model, right? So first, let's state the population model. We say the population model is mu of y equals to beta 0 plus beta 1 x1 plus beta 2 x2 until beta k xk, right? Okay, remember what we tested for the simple regression. Still remember? We had the mu y equals to beta 0 plus beta 1 x, right? So we want to test about, so this is for the simple regression, right? Okay, so we want to test about beta 1 equals 0 or beta 1 not equals to 0, right? So we say if beta 1 equals 0, then this term will be gone, then there's no relationship between x and y, right? Okay, so now I want to first test about the overall significance of the regression. All right, so what does that mean? I want to test if I look the whole regression model, whether this regression makes sense or not make sense. So I want to test about the overall significance of the regression. All right, so that means I want to test whether, it doesn't matter which explanatory variable it is, I just want to test overall whether there is any relationship between the explanatory variables and the response variables. So it will be the same idea that we want to test whether beta 1 equals to beta 2 equals to beta 3 until beta k, all of these betas are 0, or at least one of the betas are not 0. Alright, so let's see if beta 1 equals to beta 2 until beta k, all of them equals to 0. That means this term will be gone, right? This term will be gone, this term will be gone, all of these terms will be gone. That means there will be no relationship between the explanatory variables and the response variable. Alright, so that means if the null hypothesis is not rejected, that means what? That means there is no significant, well, let's say this way. Let's say the regression is not significant. Right, the other way, if at least one beta is not 0, at least one beta is not 0, that means at least one explanatory variable has the relationship with the response variable, right? So for this case, overall the regression is significant, or we say the regression is meaningful, right? So here we are testing about overall significance of the regression. I don't care about which one, I care about the whole thing, right? I care about the whole explanatory variables and the response variable. All right, so how we can test about these, right? So here we will use a F-test, right? So this is another test. We talked about z-test, we talked about t-test, we talked about the chi-square test. So this is another test, we call it is F-test. But of course, for the second step, before you calculate the test statistics, you need to check the assumptions, right? So actually we have already checked them, we have already talked about the assumptions, right? And next we will talk about the F-test statistics. Right. Before we talk about the F-test statistics, we need to make an introduction about this table. All right. So to get the F-test statistics, this is the formula of it. Right. F-test statistics is equals to MSR divided by MSE. So what is MSR? So MSR is SSR divided by K. And then MSE is SSE divided by N minus K minus 1. So this looks like 100% new to you, right? So what is SSR? What is SSE? What is MSR? What is MSE? Right, so let's talk about this one by one. So first, this table is about our, let's look at our outputs. Right, so remember before in our simple regression, we only talked about the summary of fit table and the parameter estimate table. We skipped this table. We call this is the ANOVA table, right? So actually these things are got from this table. Right, so now let's talk about the first one, MSE. So what is MSE? This is the formula of it. So actually it is the residual squared in the sum of them, right? So we call it is sum of squared residuals. That easy, so we short for SSE. Alright, so be careful. Sum of squared residuals is SSE. It is not SSR. Alright, because what? Because the residual is also called the error term. Alright, so the sum squared residuals will be the SSE. Alright, so that will be enough for you. Alright, so what is SSR? Right, so look at this formula. It is actually the y hat minus y bar. So when we know that y hat, right? Y hat is the predicted value of y. What is y bar? The y bar is mean value of y, right? So we use the y hat minus y bar and then squared and then sum of the squared. So here we call it is the regression sum of squares, or sometimes we call it is sum of squared regression. SSR, short for SSR, right? So until now you may just got scared about these formulas, so you don't need to worry about these formulas. You can get the SSE, SSR from the output. I will not require you to calculate all of these formulas. It will take you about, if you have 1,000 observations, then you may take 1 or 2 whole days to calculate the single one, right? So I will not ask you to calculate it. You just kind of get the idea how this come from. All right, so since we use the y hat, that's why this y hat is based on the regression, right? So we call it is sum of squared regression, so it is SSR. All right, the next one is called SST. All right, so SST is sum of y minus y bar squared. So here will be called the total sum of squared. Alright, so we call it is SST. Alright, so we have 3 sum of squares, right? Then we have this relationship. We say sum of squared total will equals to sum of squared regression plus sum of squared of the residuals. Do you feel familiar about this relationship? That's the same thing when we talk about R squared. Remember that? So R squared tell you the proportion of variation that is accounted by the regression, right? So actually the R squared just take care of this part, right? So this part will be accounted by the regression, and the other part of the variation will be caused by the random error, which is our, I will prefer to use error because the notation is quite confusing, right? So the other part of variation in y is caused by the random error, right? And then SST just show you the total variation in y, right? So still remember this relationship? We say the total variations in y can be divided into 2 parts. The first part will be the variation in y that can be accounted by x, or counted by the modeling, which is by the regression. And the other parts will be, even though the x values are the same, you may have different y values. So for this case, it is just because of the random error. Alright, so actually these three things just to show you the total variation in y that can be divided into two parts. The first part is about the regression, the other part is about the random error. So remember this formula. It is SST, the total sum of squared, equals to sum of squared regression plus sum of squared of the error. We say SST equals to SSR plus SSE. Alright, for these three sum of squares, they have the corresponding degree of freedom. Alright, so let's try to remember the degree of freedom from the bottom to the top. Right, so sum of square total, that means the total variation in y, and then the degree of freedom is just a n minus 1. Alright, then what is the degree of freedom for the regression sum of squares? So for regression, we totally have how many explanatory variables in our regression? Remember, this is our regression model, right? So how many explanatory variables are in our model? We totally have k of them, right? So we have the degree of freedom for SSR is just a k. Alright, okay, and then the degree of freedom of SSE will be n minus k minus 1. So where does this come from? We have this relationship, right? And then we have the corresponding degree of freedom for SST is n minus 1. SST equals to SSE plus SSR. Right, or reversely, let's do the same, let's say the same order. Right, so we say SST equals to SSR plus SSE. Right, now take care of their corresponding degree of freedom. So the degree of freedom for SST is n minus 1. Will equals to the degree of freedom of SSR plus the degree of freedom of SSE. So the degree of freedom of SSR is just a k. And then what is the degree of freedom of SSE? You just use n minus 1 minus k, right? So the degree of freedom for SSE is just a n minus k minus 1. Alright. Okay, now we kind of got what is SSR, sum of square regression, divided by k. So where does this come from? This is SSR divided by its corresponding degree of freedom. Then we call it is mean squared regression, which is we call it is mean squared regression. Why we call that? Because we totally have some of these squares, right? Divide by how many of them. So degree of freedom is kind of showing you how many of them they are summing together. Alright, so that means the MSR is called the mean squared regression. And then divide by SSE, divide by the n minus k minus 1. So what is that? SSE divided by the corresponding degree of freedom will be MSE, the mean squared error, or the mean squared residual. Right, so now do you make any sense for this formula? At least you know what are they, right? So we say MSE is just a mean squared, let's see, mean squared error. All right, the problem is we cannot find, or we cannot calculate them by hand. What we need to do is we use the ANOVA table. All right, so here I just use this ANOVA table, the same here, right? Okay, so ANOVA table will always have 3 rows. All right, so the first row is called the model. So that means this model is about the regression, right? Next one is about the error. That means we just say it is about the error. And then we have the total. Remember, we also have 3 things here, right? We have SSE, SSR, and the SST, right? So that means this is corresponding to the regression, which we call it is SSR, right? This is about the error, so this is about SSE. And this is about the total, so this is SS total. All right, so we have 3 rows for each sum of squares. And then we'll have the corresponding degree of freedom. So how we get this? This is the ANOVA table for the why we have this 52. Yeah, I think this is just about the last example. I made another data set. All right, so just focus on this table first. All right, so that means the degree of freedom for the model is 2. That means this 2 is K, right? Because what? Because the degree of freedom for SSR is K, right? So that means K equals to 2. And then, but for this one, the degree of freedom for the error is 49. That means it is n minus k minus 1 equals to n minus k minus 1 will be 49. Right, so what is the next one? The SST, right? SST has the degree of freedom is n minus 1. So that means n minus 1 equals to 51. That means what? That means you have k equals to 2, and then you have n equals to 52. Because n minus 1 is 51, then n equals to 52. All right, so this is the first column of actually it's the second column of this ANOVA table. The first column is called the source. The source of what? The source of the variation. So the source of the variation can be divided into 2 parts. One is by the regression, the other part is about the error, right? And then we have the total variation. All right, and then the next column is called the sum of squared. That means the first one is about the model, so it is SSR. So it is already calculated, it is already given to you. So this is SSR. The next one will be SSE. Next one will be SST. So what is the relationship between these 3? SSR plus SSE equals to SST, right? Okay, and then next column will tell you what is the mean squared. What is the mean squared? right? So the first one will be the mean square of the regression, which is MSR, right? So how you get this MSR? MSR equals to SSR divided by its degree of freedom, which is our K, right? So for our case, we'll be using this one, this sum of squared regression divided by 2, which is the degree of freedom. We'll get this number, right? So this is the relationship in this table, right? And then next, this 22252, what is this? This is mean squared error, right? So this is MSE. Remember what we had, we talked about this before, right? So this is the MSE, which is just a SSE divided by the corresponding degree of freedom, which is n minus k minus 1. So for our case, we use this number divided by 49. You should have this MSE. Alright, and then what is F-test statistics? It was given to you. The F-test statistics is just the MSR divided by MSE. So this divided by this will be your F-test statistics. And then you will have the corresponding p-value. Alright. So this is the ANOVA table. So this ANOVA table tell you the analysis of the variation in Y with the two sources of the variation. So you have total variation in Y that can be divided into two parts, so that you have SST equals to SSR plus SSE. You have the degree of freedom with the same relationship. You have the degree of freedom of SSR plus the degree of freedom of SSE will equals to the degree of freedom of SST. Alright, and then the next column is about MSR. MSR is just a SSR divided by degree of freedom. And then MSE will be SSE divided by the degree of freedom. And then F-test statistics. F-test statistics will be just a MSR divided by MSE. That's it, right? And then you will have the corresponding p-value. So this p-value is based on the F table, right? So here I will not ask you to find the p-value based on the F table, because I can show you what is the F table, right? But before you look at the F table, we need to F table, F distribution, right? F distribution has 2 degrees of freedoms. So they have 2 degrees of freedoms. We have the numerator degree of freedom and denominator degree of freedom. Why we have 2 degrees of freedom? Remember, F-test statistics equals to MSR divided by MSE, right? So the degree of freedom for the numerator is k. The degree of freedom for the denominator will be n minus k minus 1. Right, so we have 2 degrees of freedoms. So here you need to be careful about it. Alright, and then the way to check the F table to get the p-value is depending on kind of a little bit complex. So I don't want to show you here to make you confused. So we just use the p-value in our output to make our conclusion. Right, so this is the notation of the F. Actually, this is the F star. This is just the F value of it, right? So we have 2 degrees of freedom. We need to say the numerator degree of freedom first, and then with a comma with the denominator degree of freedom. Right, so What is K again? K is number of explanatory variables included in this regression. Alright, so once we have the f-test statistics and p-value, next we can make the conclusion based on the p-value, right? So again, if p-value is less than alpha, then we reject the null hypothesis. If we reject the null hypothesis, that means at the beginning we say what? If we reject the null hypothesis, that means we have enough evidence to support the regression is significant, right? So we say we have enough evidence to support that the regression is significant, right? So I will skip for the other side, right? P-value larger than alpha, then do not reject the null hypothesis. We do not have enough evidence to support the regression is significant, right? Okay, so let's think about the whole idea here. We say f-test statistics will equals to MSR divided by MSE, right? MSR is the SSR divided by its degree of freedom, which is just a K, and then MSE will equals to SSE divided by N minus K minus 1. Alright, and then here we'll have some relationships, right? So we have the first relationship is we say SST equals to SSE plus SSR, or reversely, right? And then we say the degree of freedom also follow the same relationship, right? So let's use the same format in the note. So SST equals to what we said as, what is the order of it? SSR first, okay. So SSR plus SSE, right? And then the degree of freedom for these three will be SST, degree of freedom will be N minus 1, will equals to SSR with the degree of freedom will be just a K, right? And then plus SSE, degree of freedom will be just a N minus K minus 1. Alright, so this is the relationship between these three sum of squares, right? So in your in-class practice, I may make some of them blank. Maybe I have this blank, but I give you this two. That means how you can make this degree of freedom, how you can calculate this degree of freedom. You use 51 minus 49 should be equals to 2. Or I can make this blank, that means you use 2 plus 49 should be 51. Or I can make this blank, but will give you this 2. Or this 2 can both blanks because what? Because you can calculate based on the SSR divided by the degree of freedom, SSE divided by the degree of freedom. Right, so you need to understand the relationship between these three. Alright, okay. So you will have the in-class practice before this. Alright, so we have already done with the, we say it is the overall significance of the regression, right? So this is about the hypothesis test for the overall significance of the regression. So in the next video, we will talk about another hypothesis test followed by this hypothesis test. All right, so see you in the next video.